Chapter 3, Part 1, Energy. So when we begin to consider energy, the first quantity that we need to investigate is called work, W-A-R-K, work. And work in physics has a very specific meaning. It doesn't mean exhaustion. And so let's get on with what work means in physics. The work done by a force acting on an object is equal to the magnitude of the force multiplied by the distance through which the force acts. Okay, so here's an example. Someone can push against a wall and push against a wall as much as he can. In the top figure, there's no work done. Although he's exerting a force horizontally, no work is done in the top figure. But as soon as the wall moves in this case, so the wall has moved through some distance while a force was acting, then the product of the force used and the distance the wall moved becomes the work done. So here's the equation then. So the equation for work is W then for work is equal to F times D. Notice that we've also used W for weight, so you can tell whether or not you're talking about weight versus work, depending on the context of the problem. And now this is my structure, that if you're going to multiply two quantities, it behaves as if you're multiplying two parentheses. Okay, so work done equals to the applied force to the distance which it acts. We've already said that. Only the part of the force parallel to the displacement contributes to the work done. Now, what is the unit of work? The SI unit of work is the joule, Joule, joule. So 1 joule is equal to 1 Newton multiplied by 1 meter. 1 Newton times 1 meter is equal to what we call a joule, a J, and we use capital J. So but Newton is a derived unit, which is a kilogram meter squared per second squared. When you multiply a kilogram meter squared per second squared times a meter, you get a kilogram meter squared per second squared. That's the true unit of the joule. Okay, let's go on. Work done against gravity. Suppose then that a force is used, and while it's being the force travels through a distance d. But force then due to gravity is m times g, and let d equals h. So we will use the formula. Work done by gravity is equal to mgh. There it is there. Illustration. Suppose then that a person applies a force mg and moves a distance a. The work done is mgh. Just that simple. The work done by force due to gravity, if the object is at some height h already and the body moves down a difference, moves down this distance h, then work is done by gravity in this case. An example. In comparing a horizontal force versus gravity. A horizontal force of 100 newtons is used to push a 20 kilogram box 10 meters across the floor. How much work we have to do in order to implement this process? And compare that with B. How much work is needed to raise the same block 10 meters? The answer is here. So in the first case, the force is 100 newtons and it travels a distance of 10 meters. 10 times 100 is 1,000. A newton times a meter is a joule. So 1,000 joules. Now compare that with the second case. The mass is 20 kilograms. The value of g, the acceleration due to gravity, is 9.80 meters per second square, and it moves that same height 10 meters. Now the work done is 1,960 joules. More work is needed in this particular case. Okay. Power is another quantity that is used frequently in physics. Power is the rate then of doing work. So it's work per unit time. That's the definition of power. And you will find that we use it in many different situations throughout this course. Okay, so in words, work per unit time. In symbols, W over T. The unit of power, the SI unit of power is the watt, W-A-T-T, and we use the symbol W. So once again, W is being used again. W is used as weight. It's also used for work, and now it's being used for watt. But in each case, you can distinguish what is meant by the context of the problem. So 1 watt is equal to 1 joule per second. We also use another old unit for power. It's called a horsepower, which is 746 watts. Automobiles are rated in horsepower, the horsepower power of the engine of the automobile. What is energy? Energy is that property of something that enables it to do work. So interestingly, we gave the definition of work first, and now we are relating energy to work. So energy is that property of something, some matter, or some person, or something that enable it to do work. Whatever that something is, it has to be able to deliver some force if it's going to be converted to work through some distance. There are different forms of energy, as you will see. The first one that I want to introduce you to is called kinetic energy. This is energy associated with motion. The energy of a moving object is called kinetic energy. And kinetic energy depends on two factors, the mass of the object and its speed. And here we write then as the symbol for kinetic energy is this juxtaposition KE. So KE then is equal to 1/2 mass times the velocity squared. It turns out this is an important definition. And yes, the square is needed for the speed, and the 1/2 is needed in front of the symbols so that we will see systematically how kinetic energy gets converted to work. Let me go on. An example. What is the kinetic energy of a 1,000 kilogram car whose speed is 10 meters per second? Plug in the numbers here, go through the mathematics, use your calculator, and you get that the kinetic energy is 50,000 joules or 50 kilojoules using the prefix. This shows then a depiction here, a car moving at a certain velocity, 10 meters per second squared, moving to our right. It has a kinetic energy of 50,000 joules. If the same mass of the car is moving much faster, 3 times faster in this case, 30 meters per second, notice that the kinetic energy is not just 3 times more, but it's tremendously more, 450,000 joules. An example further. Now, how kinetic energy can get converted to work. If the 0.4 kilogram hammer head is moving at 4 meters per second when it strikes a nail, uh, strikes a nail 5 millimeters into a piece of wood, what is the average force on the nail? Hint, change in kinetic energy equals work done. So that's what we have here. The kinetic energy is 1/2 mv squared, and that's equal to work, which is equal to F times D. We're going to move the D to the left-hand side of the equation and write then that F is equal to 1/2 mv squared, and that's what we have here. So this is an illustration of the hammer. This is the formula then. So we put in the numbers here, and the work comes out to be 9,600 newtons. An illustration of this. Let's see. Okay. Okay, let's go to the next section here. Now I want to introduce potential energy. Potential energy is stored energy. And let's talk about gravitational potential energy. Although we can have gravitational potential energy, spring potential energy, and electromagnetic potential energy. We will only consider gravitational potential energy. For instance, if you raise an object of a pulley, a certain height, you raise a stone, it has potential energy, and it can crash into the ground if you let it go. So how much work done is done by potential energy? Once again, work is equal F times D, and it's equal to mg times the height that the object is raised above the reference level. So it's mg times h. Here it shows. If you have this mass here at the reference level, you raise it a certain height, h, it has potential energy when it's held at that particular height of mg times the height that it was moved. And this is an illustration of calculating the potential energy. What is the gravitational potential energy of a 1,000-kilogram car on top of a 45-meter cliff? You put in the numbers, you multiply here, you get 441 kilojoules. Energy then can be transformed. Energy can be transformed from one form to another. You can change kinetic energy to potential energy. You can change potential energy to work, etc. It can go on and on. This is shown now. At the top of the hill, the energy is in the form of potential energy. At the bottom of the hill, it's in the form of kinetic energy. It goes back and forth. An illustration with a pendulum. If you have a pendulum at its equilibrium point, you raise it to some height h, then it has the maximum potential energy is at this point. The maximum kinetic energy is at the low point. Okay. And we illustrate here with a ball. The person is going to bring the ball over to his face. Okay. And there are different forms of energy, as you will see, and we will have occasion to talk about many of these other forms throughout this course. That brings me to the end of this presentation.